area under a curve. This is application of definite integrals. The given function is integrated and evaluated by substitution. First of all, the upper limit followed by the lower limit. And then we now find their difference. Here is part of a curve of the function y equal to f of s. We are interested in finding the area under this curve between the point A and B. The ordinate here is S1 and then S2. So we are interested in finding the area of this dotted portion between S1 and S2. The area under the curve between the point A and point B. In order for us to find this area, we are going to use this diagram above. The area A under the curve AB about the x-axis is given to us by the formula A equal to the integration from the point S1 to the point S2 of y dx. The y dx is the same thing as your f of s dx. After integrating this function, we will have a value from where we now substitute the upper limit s2 and then of course substitute the lower limit s1 and find their difference. It is this result that will give us the area under the curve AB as shown above. That is the dotted part of this curve. Similarly, the area A of a curve adjacent to or about the y-axis is area A equal to the integral of s dy from y1 to y2, which is equal to the integral of f of y dy from y1 also to y2. This is represented by the diagram below. Look at the diagram here. Here is a curve, and this curve is s equal to f of y. Now, we are looking at the area between this point y1 and y2, the shaded portion here. Okay. To find the area of this shaded portion, that is why we have to use the formula s dy from y1 to y2 as indicated above. So this is a situation where the curve is adjacent to the y-axis or is about the y-axis. We may also need to consider another case of area under the curve. In a situation where the curve is below the x-axis, especially between the point A and B here as indicated, you discover that the curve is below the x-axis. At this point in time, we are saying that the curve is negative below the x-axis between the point A and B. In order to find this area here that is below the x-axis, we say that your y, which is f of s, is negative in the range A to B. So to find the area, it will be equal to minus the integral of y ds from the point A to the point B, which is equal to minus the integral of f of s ds from the point A to point B. Because it is below the x-axis, that is why we have introduced the negative sign in the formula. Here is another situation. If y is equal to f of s is both positive and negative, the total area will be found in two parts. Here is an illustration showing a curve that is both positive and negative. And we are required to find the area shaded. Part of the shaded area is positive and one is negative. Negative because it's below the x-axis. As you can see, from the point A to B is positive, from the point B to C is negative. And the function is y equal to f of s. So all we need to do to find the area of this shaded portion is to integrate the function f of s between the point A and B, and then subtract the integration of f of s between the point B and C. Thus, we have area A equal to the integral of f of s with respect to s between the point A and B, minus f of s ds, the integral of f of s ds between the limits B and C. I want you to note that we must sketch the curve of the function before using integration to find the area. The reason is because the curve may be positive and also negative at the same time. We look at another situation of area under a curve. So we look at area under a curve between any two curves. Here we have y equal to f of s and y equal to g of s can be found if the points of intersection or the limits are known. Okay, here is a diagram describing a situation explained above. This is the first figure where we have two curves. One is y equal to f of s and the other one is y equal to g of s. And then we have the shaded part of the intersection of the curves. Now we are to find the area between the points s equal to A and s equal to B. You will observe clearly here that one of the curves occupies a larger space than the other. So the curve that occupies a larger space will come first, followed by the curve that occupies a smaller space. So that when you subtract that, you will have the region that is their intersection or shaded here. So as you can see, this curve y equal to f of s covers a larger space between this point A and B than the curve y equal to g of s. If you look at it carefully, you can see now this is the space covered by this, while this one covers up to this point. So in order for us to find the area here, we find the area of the larger one and find the area of the smaller portion and then subtract. So we eventually have in figure 1 that A, the area, will be equal to the integral f of s ds from the point A to B minus the integral of g of s, which is the smaller area occupied by that, ds from the point A to B. Now similarly, we have a situation here where we have a curve and a line. So this is a situation of linear and quadratic, let's say, so to say. So in this regard, you have here that your y equal to f of s is occupying a greater portion than your y equal to g of s, which is the function or the equation of the curve. So in other words, between the point A and B, we can find the area that is shaded by writing A equal to the function f of s ds, the integral of this function f of s ds, which occupies the larger portion from the point A to B, minus the integral of the function of the curve, which is gs with respect to s, and then from the point A to B. So when we evaluate them accordingly, we will find the area that is shaded. We'll take the first example, number 1. Here is a graph, and then there's a region that is shaded. They said that the graph of y equal to s squared is as shown above. The shaded area is dash. Our solution. Observe very carefully here that there are two equations involved in this graph or in this diagram. We have one, the equation y equal to 16, or what we say f of s is equal to 16, the linear equation there. Then we also have another equation which is y equal to s squared, describing the curve. And you can see that the linear equation occupies more region than the curve. especially between the point s equal to 0 and s equal to 4. So the point of our integration, the limits of our integration or finding the area, so our limit is s equal to 0 and s equal to 4. So we have the lower limit and the upper limit. So how do we find the area that is shaded? Therefore, the area A shaded will be equal to integrating from 0 to 4 of the linear function, which is f of s equal to 16. So that is 16 with respect to s. And then, of course, we will also now subtract the region where the curve occupies, and that is from 0 to 4 of s squared with respect to s. Now, let's integrate this. If you integrate 16, the s is equal to 16s. And then, of course, we have the value evaluated from 0 to 4 minus, integrate this, you have s cubed all over 3. And we evaluate this also from 0 to 4. Although if we say 16s minus s cubed over 3, all evaluated between 0 to 4, we also have the same result. But to be on the safe side, we are taking them 10 by 10 so as to avoid a possible error. So here we have 4 we go into this, that's 4 times 16 times 4. Of course, 0 times 16 will be 0. Then, of course, we have minus 4 into this, 4 raised to the power 3 is 64. And then everything will be divided by 3. So this eventually will give you your 64 minus 64 all over 3. If you now find the value of 64 minus 64 all over 3, you will eventually have this to be equal to 128 all over 3, of course, square units or unit square. So you can say square unit because we're talking about what? Area. So that gives you the solution to the problem. You have calculated the area under the curve y equal to s squared and the linear function y equal to 16. Example number 2. Find the area between the curve y equal to s squared minus s, the s axis and the ordinates s equal to 0 and s equal to 2. Solution. First and foremost, you will recall I told you that you have to sketch the curve so that you are able to determine the region where the solution lies. It can be positive and at the same time negative. So we find the table of value, prepare a table of value, s and y. Let's start from s equal to minus 2, s equal to minus 1, s equal to 0. We take 1, we take 2, we take 3. There are other ways of sketching the curve, but let's do this. Then when s is minus 2, eventually you substitute the value of s equal to minus 2, your y will be 6. When it is minus 1, this is minus 1 is 1, minus that, this will give you 2. When s is 0 and y is 0, when s is 1, our y is 0, and then when s is 2, 4 minus 2 is 2, and when this is 3, 9 minus 3 is 6. Okay, with this we are going to sketch the curve, and then we have, let's take a sketch of the curve. We have something like this. Let's take the sketch of the curve. Alright, this is our s axis, and then this is our y axis, and then let's say this is point minus 1, and this is point minus 2. So assume now we have this is our 0, we have a point 1, we have a point 2, and we have a point 3, and then we have something like this, 2, 4, and 6. Now when s is minus 2, this is your 6, minus 1, this is your 2, and this is your 0, and this is your 0 again, and this is your 2, and then when it is 3, this is 1, 2, and 3, and this is 6. So connecting that together, you join it, you go down, and then it goes up like this. And once again, we are looking between, so we actually have between 0 to 1 below the x-axis, and from 1 to 2 we have above the x-axis. So we have both negative and positive. This is your curve y equal to x squared minus x. So this done, what do we do next? We are now going to integrate our given function from 0 to 1 and from 1 to 2. So how do we go about that? Our area will be equal to integrating from 0 to 1, and it becomes minus because it's below the x-axis, and the function is x squared minus x with respect to x, and then plus integrating from 1 to 2, the same function x squared minus x with respect to x. Now that you have gotten that, what do we do? This becomes minus, don't forget this minus, then let's open a bracket. If you integrate this, you have x cubed all over 3, and if you integrate this, you have x squared all over 2. You close the bracket and evaluate from 0 to 1. Plus, we do the same thing here, open the bracket, and that is x cubed all over 3 minus x squared all over 2, evaluated from 1 up to the point 2. Beautiful. So at this junction, we have minus, open the bracket, 1 here will give you 1 all over 3, and 1 here will give you minus 1 all over 2. Okay? So this is what we have in this case. And of course, when you substitute 0, everything there will be 0. So we don't need that again. We'll close that bracket. Let's see what happens next. Now this is plus 2 raised to the power 3 is 8 all over 3 minus 2 raised to the power 2 is 4 all over 2. Then when you have done that, the upper limit minus, open the bracket again and put this. This is going to be 1 all over 3, and then minus 1 all over 2. So let's open the brackets all together. We have minus 1 all over 3, and then plus half, and then we have plus 8 all over 3, and we have minus 2, or rather we'll leave it as minus 4 all over 2, and here is minus 1 all over 3, and we have plus 1 all over 2. So you now simplify this as best as you can. Let's use our LCD to be 6. So we can have our LCD as 6. So this becomes minus 2. And this is plus 3. And this is plus 16. And this is minus 12. And then this is minus 2. And then this is plus 3. Everything here all over 6. Good. So let's see. This we add up to what? 16. This is 1. 17. 5. Minus 2. That's 3. 3 plus 3 is 6. So we have 6 all over 6. And the final answer is equal to 1 unit. So we have the area under the curve is 1 square unit. 1 square unit at the solution. 1 square unit at the solution. Example number 3. Find the area between the curve y equal to 2x squared and the y-axis, cut off by the lines parallel to the x-axis through the points on the curve where x equal to 1 and x is equal to 3. Now let's start our solution. First and foremost, let's sketch what the graph will look like. We are giving, this is your x-axis, this is your y-axis, and here is the curve. We're looking at maybe y1 here, and we're looking at y2 there, and this is your y equal to 2x squared. This is the origin. Our interest is to find the area between y1 and s1. This is the case we have here. First and foremost, let's look at the limits. For y1, it will be equal to 2 multiplying s equal to 1 all squared, and that will be equal to 2. And then for y2, the point there will be 2 multiplying 3 all squared, and that is equal to 18. So we're going to integrate our function from 2 to 18. But then, remember that this is on the y-axis. So we have to make s the subject of the formula. So we have that from y equal to 2s squared, our s will be equal to y all over 2, and everything here under square root. So in other words, our solution, therefore, the area under the curve will be the integration from 2 to 18 of our s dy. And then your s now is the integration from 2 to 18. Your s is root y, okay, all over root 2. And then with respect to y. So this will be equal to, so our a will be equal to, the value is 1 all over root 2. We now integrate our root y with respect to y. I hope you remember that this is 1 all over root 2, the integral of y raised to the power half with respect to y. Remember the laws of indices. So when we integrate this, you will have this as 1 all over root 2 y raised to the power, add 1 to half to give you 1.5, and 1.5 means 3 all over 2, and then all over 3 all over 2, and then after that you will evaluate this from 2 up to 18. That's what you have. Now, this can simplify further, and then we now have this as 1 all over root 2 times 2 all over 3. This 3 over 2 becomes 2 over 3. And then here is 18 raised to power 3 all over 2. Minus, do the same thing here. This is 1 over root 2. And then, of course, times 2 all over 3. And then also times 2 all raised to power 3 all over 2. So this is what we are going to simplify. You can do this by having this as 2 all over 3 root 2, and then times 18 is 9 raised to power 3 over 2 times 2 also raised to power 3 all over 2. Minus the same thing we have there, which is 2, 1 times 2 all over 3 root 2, and then again times 2 raised to power 3 all over 2. Okay, let's still go. And then we have this. This is common, so we can pick it out if we want. Otherwise, we can still leave this, and we have this as 2. Let's actually pick it out. 3 root 2, and then open a bracket. Our 9 is the same thing as 3 raised to power 2. Multiply this by 3 all over 2. And then our 2 raised to power 3 over 2 is the same thing as 8 raised to power half. 2 raised to power 3 is 8, then the power half. And then this is minus the same 8 also raised to power half. Close this. Okay? So let's see what will happen further. We now have this to be equal to your 2 all over 3 raised to power 2. Now open the bracket. What does this stand for? 2 we cancel 2, so remaining 3 raised to power 3, and that is 27. And of course, times, this is 8 raised to power half, means 4 times 2 raised to power half. So and 4 raised to the power half, and then times 2 raised to the power half. Minus the same thing here, 4 raised to the power half, and then times 2 raised to the power half. So that this will give us a value that is equal to, we now have this as 2 all over 3 root 2 into the 27 times 4 raised to the power half is 2, and then this is times root 2 minus the same 2 also times root 2. Let's see what happens. So this becomes 2 all over 3 root 2. This time this will give us 54 times root 2 minus 2 root 2. Subtracting, we have 2 all over 3 root 2 times 52 and then root 2. Of course, root 2 will cancel root 2. So we have 2 times 52 is 104, and then everything here all over 3. That will give us 3, and that is 4, remaining 2 all over 3. So we will find the area, and we have it as 34 2 over 3 square units. Let's look at the volume of solid of revolution. A cone, a cylinder, a flower vase, for example, have a central axis of symmetry. They are examples of a solid of revolution. Let's take a look at a cone here. Now you see this line and this line. If there's a plane that cuts through this axis, that plane will cut the shape here, the cone, into 2 equal parts. Similarly, if there's a plane that cuts through from this point, it will also bisect the cone. So this line, or this line, is the central axis of symmetry. Here is a cone. And maybe to generate this cone, to form this solid, a part of the curve was rotated through an angle of 360 degrees. We shall see that explanation below. So if the area under a curve is rotated completely about the x-axis or y-axis or 360 degrees or 4 right angles, then the volume of solid generated is calculated as follows. Take note, we're talking about the volume of a solid generated, so that when you rotate part of that curve, part of that area under that curve, through an angle of 360 degrees, a solid will be formed. And we are interested in finding the volume of that solid that is formed through that process. Now, we have 2 situations here we are going to consider. The first one is represented by this diagram, and the region shaded is rotated about the x-axis through an angle of 360 degrees or 4 right angles, or rotated completely. To find the volume generated by this, we write volume V is equal to the integration from the lower limit to the upper limit, that is that portion from here to here, and then we have power, and then we have y squared, and then of course with respect to s. This is the formula for finding the volume generated by this object or this function at the point that is shaded through an angle of 360 degrees, when this actually is rotated through the x-axis. So this is about the x-axis. That is this case. Now, remember that our function is y equal to f of s. That is the curve. Over here too, the second case, you have the curve is the same, y equal to f of s. Now you will now see clearly here that this is rotated about the y-axis. So in this regard, our volume will be equal to from the limit y1 to y2, and then of course we have the same power, and this time s squared with respect to y. So this is a rotation about the y-axis. There are other cases we are going to look at, but specifically these two cases will suffice for now. So let's look at how to calculate the volume generated either about the x-axis or about the y-axis accordingly. Example number 1. A bowl is designed by revolving completely the area enclosed by y equal to s squared minus 1, between y equal to 0 and y equal to 3, around the y-axis. What is the volume of this bowl? Solution. First of all, underscore the statement around the y-axis to let you know that the formula you will use to find this volume, V, will be equal to the integration from y equal to 0 to y equal to 3 of your power and your s squared with respect to y. Now, once you have recognized this, you know that you were giving y equal to s squared minus 1. In other words, our s squared is equal to y plus 1. So we now replace, therefore, the volume will be equal to, you can bring out the power because it's a constant, and then 0 to 3, and then our s squared now is y plus 1 with respect to y. Integrating this, you will have your power, and then of course, you also have to integrate y, that will give you y squared all over 2. To integrate 1, that will give you y. And everything here will be evaluated from 0 to 3. Now, that said, we have power, and then evaluating that, 3 here will give you 3 squared over, 3 squared is 9 all over 2 plus 3, and then of course minus 0, and eventually this is 4.5. 4.5 plus 3 is 7.5. 7.5 is 15 all over 2 of power cubic units. That gives you the volume that is generated. Example number 2. The portion of the curve y equal to half s squared from s equal to 0 to s equal to 2 is rotated about the s-axis through 4 right angles. Find the volume generated. Take note, through 4 right angles means it is rotated completely. So our solution here, also take note of the fact that it's about the s-axis. So knowing that it's about the s-axis, our volume generated between s equal to 0 and s equal to 2 will be power into y squared and then times the x. Okay, now that we have this, our interest is to find y squared from y equal to half s squared. So y squared will be equal to half s squared all squared, leading you to have 1 over 4 s raised to the power 4. Therefore, the volume will be equal to taking power out and taking your 0 to 2, your y squared now is 1 over 4 s raised to the power 4 with respect to s. And this can also lead us to have 1 over 4 power and then integrating from 0 to 2 of s raised to the power 4 with respect to s. Okay, and this can be 1 over 4 power, integrate s raised to the power 4, that is add 1 to 4 to give you 5, and then divide by 5, and then of course evaluate this from 0 to 2. That will give you 1 over 4 power. If you evaluate by replacing s by 2, 2 raised to the power 5 is 32 all over 5. And then, of course, 0 will be minus 0, so it doesn't change it. 4, we cancel 32, that will give you 8. And the final result is 8 power all over 5 cubic units. That gives you the volume that is generated. Example number 3. The curve y equal to s squared minus s below the s-axis is rotated about the s-axis to form a solid of revolution. Find its volume. Find its volume. Now, our solution, be careful here. There is a curve, and we need to sketch the curve so that we'll be able to see the area where the curve is below the s-axis. So our first major step, we take our y equal to s squared minus s, and then of course find the values when s is equal to, let's take minus 2, minus 1, 0, 1, 2, and 3, so that at the end we have here, this will be, when s is minus 2, substitute, we have done something like this under area under the curve, so we now know what the values here are, and then this is equal to 2, and that is equal to 6. If you can recall, a few minutes ago we have done something like this. Now with this one, we are able to sketch the curve, which will look like this. I think at the end of the day we have something that goes and like that. So a part of this one from 0 to 1 is under the s-axis. Under the s-axis. This is your y-axis. This is your curve y equal to s squared minus s. By the time you plot the points, you will now have this region below the s-axis. So it is this one, this portion that is rotated completely. So it means that our integration, our limits will be from 0 to 1 of the function, so that we can find the volume that was generated through this means. So here our volume will be equal to, remember that it's rotated about the s-axis. So our volume will be from 0 to 1, and if it's about the s-axis, you will recall this is pi y squared dx, about the s-axis. So what does this stand for? You have your y already there, so we now have that from y equal to s squared minus s, our y squared will be equal to s squared minus s all squared. If you open the bracket, this is s to the power 4, this is going to be plus s to the power 2, and then this times this is your minus 2s raised to the power 3. So we can rearrange it in such a way that the powers should be ascending or descending, so we can actually write our y squared is equal to s to the power 4 minus 2s to the power 3, and then plus s squared. This is the order in which you can write your polynomials. Alright, from this level, we are now going to integrate the function accordingly. So our v will be equal to, bring out to power, and then integrate from 0 to 1 of y squared, which is s to the power 4 minus 2s to the power 3, and then plus s squared. Everything in brackets. Remember, you are integrating with respect to s. If you integrate this 10 by 10, that will actually give you power into your s to the power 5 all over 5. And this case will be minus your 2s to the power 4 all over 4. And then here will be plus your s to the power 3 all over 3. And then close this, you evaluate it from 0 up to 1. So this will be equal to, your power is there, and then of course when you evaluate by substituting s equal to 1, you will have your 1 all over 5, the first term. The second one will be minus 2 all over 4, okay, and the third one will be 1 plus 1 all over 3. And of course, if you substitute 0, everything is 0. So we don't need that anymore. We now have this. Let's simplify this. This is actually equal to pi into 1 all over 5 minus half, and then plus 1 all over 3. We'll close this. Now, what is common here is 30. So we have pi into 30. 5 here is 6. 2 here is 15. And then 3 here is equal to 10. This will result in pi multiplying 6 plus 10 is 16 minus 15 is 1 all over 30. So the final result is 1 all over 30 of pi, or pi all over 30 cubic units. And that's it.